Okay, so hello everybody. So to conclude our cycle of tutorials, today we're gonna talk about the last type of task that we can perform on graphs. So we have said last time, sorry, a couple of tutorials ago, that we have the node prediction task, the link prediction task, and the graph prediction task. So I briefly introduced it in three tutorials ago. But actually, today I want to talk about one technique that we can use to perform graph prediction, which is not simply based on obtaining one representation from the representation of the nodes by simply aggregating the information, but it's a more sophisticated way to obtain an embedding for the entire graph. So again, we have the graph, we have the vectors attached to the nodes. And so when we want to perform graph prediction, what we usually do is we have a global pooling function, which basically performs element-wise the aggregation function. So that can be max, min, sum, whatever invariant function. And this is used to obtain this G vector, which is the graph representation in just one single embedding. And then if you want to perform a prediction for the graph, you simply use a readout function, which is basically a multi-layer perceptron, to obtain the prediction value. So this is equivalent basically to having a super node in which that is connected to all the nodes in the graph, and using its embedding just to do to obtain the final prediction. What is the problem here? The problem is that each embedding of the nodes is treated in the same way when we perform this with this aggregation, this pooling aggregation. And so this technique does not capture the structure of the network. So we are not exploiting some sub-similarities in the graph in order to obtain this graph embedding. So to mitigate this problem, there is a pool of researchers that have introduced DiffPool, which basically uses a hierarchical pooling strategy in order to obtain the embedding for the entire graph. So DiffPool comes from differentiable pooling, and it was initially presented in the paper Hierarchical Graph Representation with Differentiable Pooling, presented at NIPS. And basically, this is the rough idea. So basically, we are going to compute hierarchical representations of the graph by aggregating on some closed nodes. We will see later what closed means. But if you look at the picture, it's pretty much straight what we are going to do here. So basically, here we have our entire graph, okay? And instead of computing simply the embedding for each node, we compute an embedding, which is for a cluster of nodes, basically. So here, as you can see, we have these three nodes, okay, that are combined together to obtain one single node representation of the cluster. With the same, we do it for other parts of the graph. And once we have done this operation, we end up having a totally new graph, which is basically a coarse representation of the previous one. And if we keep doing it, in the end, we will be able to obtain a graph which is just one node. And from that node, we can later compute our prediction with a readout function. So exactly. So the idea is that having in input the adjacency matrix and the node feature matrix, we are gonna basically stack different GNNs and pooling layers in order to do this hierarchical representation. This is a very basic scheme, but let's have a look of the ingredients here. So here we have our standard graph with the adjacency matrix and the node feature matrix. If we are talking about classification task, we are going to have a data set of graphs and its target value. So here we're going to distinguish a bit from a simple convolution operation and a full graph neural network. So basically, usually when we were talking about graph neural networks, we were talking about the convolution operation, whereas here the convolution is just a part of the entire graph structure, because we are going to use several GNNs, okay? And each GNN has several convolution operation inside of it. Okay, so just for the purpose of notation, here we're going to have that gconv expresses just the convolution, whereas GNN is an entire graph neural network with several convolutions inside of it. Again, yes, so when we refer to Z as being the output of the GNN, we are basically referring to the node feature matrix that we obtain at the last iteration K of the convolutions, okay? Okay, so at each step of this hierarchical pooling, what we want to obtain is a coarse representation of the previous graph. So basically, given the adjacency matrix and the node features of the graph, how do we cluster together the nodes of this graph? So this basically means that having an adjacency matrix, which is basically n by n, and a node feature matrix of n by times d, we want to obtain new representations A prime and Z prime, which have less nodes than the previous one, with here m less than n. Okay, this is basically what we're going to do at each step. How do we decide how we group together these nodes? Okay, in DiffPool, we are gonna learn to cluster some nodes of the graph in order to obtain this coarse representation. So the final representation of the graph is done by coarsening the graph L times here. And at each step, we are going to learn how to cluster these subparts of the graph. So in order to perform this cluster assignment, we need a cluster assignment matrix, which is a matrix of this form, SL. And it's a matrix in which we have in the rows a number of rows equal to the number of nodes at a certain step of the hierarchical coarsening times the number of clusters that we're going to have at the next iteration. Okay, so basically, if you look at the image here, we can see that okay, from the initial graph, the first time we coarsen it, we are going to obtain 5 clusters. Okay, so I don't know now how many nodes there are here. So basically, S of 1, which is the first level, is going to be a matrix which contains in the rows the nodes, and it's going to be the second dimension is going to be 5. Okay. Again, for S of 2, which means at the second level, we're going to have NL, which is 5, and NL plus 1, which is 2, as represented here. Okay. So this is the matrix that will allow us to cluster together these nodes. How do we do it? Well, basically what we take is a matrix multiplication with both the node features matrix and the adjacency matrix. Okay, so basically what we do is we multiply the node features and the adjacency by this cluster assignment matrix, and we're going to end up having a new representation in which we're going to have the number of dimensions as sorry, the length of the embedding as second dimension, and as first dimension, the number of nodes in the at that hierarchical step. Okay. So here, of course, in order to obtain an adjacency matrix, which is basically squared, we need to multiply the cluster assignment matrix before and after the adjacency matrix. To be noted here is that at each time we perform this hierarchical clustering, this is an hyperparameter. The number of clusters at each level is something that we decide at the beginning of the computation. Okay, so here again we have decided at the first level we are going to have 5 clusters, at the second 2, and the last one is always going to be 1. Okay, so remember that it is an hyperparameter. It's not something that we learn the number of clusters. That one we decided. Okay, so but how is it possible to learn this cluster assignment matrix? So basically, here the architecture inside each hierarchical step basically is the following. So basically, we're gonna obtain at each level 2 matrices by using 2 different GNNs. Okay, so here we're gonna obtain for each level. For each step, each level, hierarchical level, a node feature matrix, ZL, which basically is the output of a graph neural network that basically, this can be whatever graph neural network you prefer. So basically it could be GCN, it could be GraphSage, it can have several convolutions inside of it. It doesn't really matter. The output is what we really are going to look at. So we have 2 of them. One just for computing the embeddings, basically, of the nodes. And we're going to have a second one, which we use for calculating the cluster assignment matrix. So basically, for the cluster assignment, we have this GNN pool, which as GNN amb, it takes in input the adjacency matrix and the node feature matrix. But before, I mean, as last step, we're going to perform a softmax element-wise. So basically, this softmax, what does it do? So the output of GNN pool is going to be a matrix of basically the same shape as S. So basically, what we want to obtain is a matrix that tells us, okay, this node at the level L, where does it go at the level L+1? Okay, so to do that, we basically apply the softmax to all basically the vector obtained for the node, so which we have a probability distribution over the clusters of the next step. Okay, so again, the softmax is used to determine the probability of a node at the step L to be in a cluster at step L+1. Okay, this is useful because by using the softmax, we are going to have a bunch of probabilities that indicates how it is probable that this node fits in the cluster, and this allows for one node to be in several clusters. Okay, so it's not going to be exclusive, the fact that one node is assigned to just one cluster. Okay, and the softmax is differentiable. That's why we're talking about differentiable pooling. So since the softmax is differentiable, we can easily learn the various cluster assignment matrix at the different hierarchical levels, because we can backpropagate the error of the loss function. So this is basically what we are going to do at each step. At the last one, we're going to have simply a prediction. So basically, when we have done all the hierarchical steps ZL, we simply use a multi-layer perceptron in order to obtain the predicted value that we can then use into a loss to calculate the error, then the gradient, and then backpropagate it and update the parameters of the model. Okay. Okay, so let's switch now to the notebook in which we're going to see how things turn out in reality. Okay. Okay, let me maybe. Okay, let me make it a little bit bigger. Okay, so now I'm going to show you basically the steps that we have just seen, but let's say numerically. So basically, I'm going to create an initial node feature matrix and an initial adjacency matrix, okay, which are going to be for 50 nodes in the graph, and the adjacency is simply taken randomly. So I'm not really interested in the kind of connections that there are inside of the graph, okay. So here, okay, very simply, we create this dummy graph, and we set the number of steps. Sorry, we set the number of clusters that we want for passing from step 0, which is basically having the entire graph, to having a new version of the graph, which will have just 5 clusters, so 5 nodes, okay? So here I have specified this. And as we have seen, the components that we need are also a graph neural network, one for calculating the embedding, and one for calculating the cluster assignment matrix. Okay, so here I simply take these two parameters matrix, which is going to be WGNN-M and WGNN-Pool. I'm not going to use any particular fancy convolution already prepared in Pytorch Geometric, just because I want to give you really the feeling of these operations. So here we have our 2 functions that we need to compute. So as we can see here, we have that the input of the embedding convolution, graph neural network, sorry. So here we have the adjacency and the node feature matrix in order to obtain the Z and the S. So here we simply do the matrix multiplication that we need, as we will do in a graph convolutional layer, to obtain the two matrices for the level basically 0, or the first level, as you want to see it. Okay, then we have seen that we need a new version of the adjacency matrix and the node feature matrix for the next level. And we can do it by multiplying it by the assignment, cluster assignment matrix. And if we check the shapes, now we see that the new node feature matrix and the new adjacency matrix have a number of nodes, which is 5. I also changed the dimension, the initial dimension of the nodes, which is now 16. And actually, the adjacency matrix is 5 by 5, as we were expecting. Okay, so I took the example that is in the Pytorch Geometric tutorial about DiffPool, and I have modified it a bit. So it's not still working because I broke it just before the presentation, but once it will be uploaded, it will be a working version. So here, just to give you an example of how we can construct this in Pytorch Geometric. Okay, so in this part, we simply load the data set. So I'm not gonna go into details here. Okay, so here we have we define our 2 main components. So basically, the module DiffPool, which is gonna be responsible for these hierarchical steps, pooling steps, and the second class is the graph neural network, let's say placeholder class, that we are gonna use to define the graph neural network for the embeddings and for the pooling operation. Okay. So just to have, let's start by having a look at the DiffPool class. So here we initialize this class basically by performing, we have decided to perform 3 hierarchical steps. For each hierarchical step, we define a pool GNN and embed GNN. with the corresponding, of course, dimensions for the inner layers. So for the input, inner, and output dimensions. Here also we see that at each hierarchical step, we decide how many nodes we want. And in this case, we have decided that we are going to reduce it by 1/4 at each hierarchical step. Okay, so here we have that the first hierarchical step multiplied is the number of nodes multiplied by 0.25, and the second one is the number of nodes multiplied by 0.25 again. And as last layer, we are going to have these linear layers, which are basically the MLP needed to perform the readout, to create the readout function to perform the final prediction. Okay, so how is each of these GNN pool or embedding defined? Well, here I have created this GNN class, and in this GNN class, I have decided to put 3 graph convolutional layer convolutions. Basically, so as I told you before, here we have a GNN which has 3 convolutions inside of it, and then we have several several GNNs for each different hierarchical step. Okay. Here I have chosen GCN, but you can also use GraphSage or whatever. Okay, so here, just to have a look at the forward function, because there is something interesting here, is that so basically we have in input our graph, our node feature metrics, and our adjacency metrics of the graph. So the first thing is to actually obtain the cluster assignment matrix and the output of the GNN for the embeddings. And then we have basically to compute the next node feature and the next adjacency matrix, which is basically the 2 operations that we have seen already. But Pytorch Geometric makes it easy for us. So basically here in Pytorch Geometric, we have this function, which is called dense DiffPool, which basically performs these operations in a more controlled way than I have done. But it does it for you, basically. So you just need to give it in input the node feature matrix, the adjacency matrix, and the cluster assignment. This mask, I don't really know what it is used for, but you give it in input these 3 components, and you obtain in output the new matrices of the next layer. Then you do it again for the second layer, and then in the end we obtain the final prediction. Okay, so now it's not working, so it doesn't really make sense to have a look at it. But so basically this is all. It was a very short tutorial today, but we had just one method to introduce, and I think once you have understood all these matrix multiplications and dimensions, how they change, whatever, it's going to be very intuitive and very easy to understand, because this is a very straightforward method in which we simply learn these new matrix that we use to coarsen the graph. This is DiffPool in a nutshell. So thank you. That's all for today. And if you have any question, I will be glad to respond.
Hello, I have a question.
Yes.
Hey, sorry, I kind of joined a bit late. Maybe you covered it in the beginning. So when we say we go from, say, some number of nodes to kind of a predetermined or hyperparameter, say the pool network at level 1, are the nodes being dropped, or is it more similar to PCA where we are creating new nodes which are not explainable? right? So if we can we visualize the nodes in level 1?
Mhm. Okay, so basically, you're what they're asking is that if we retain basically some information of the previous nodes once we cluster it. Is it what you're asking?
Correct. Yes.
Good question, very good question. So to be honest, I think that is exactly what they are trying to do. So basically, uh, you want to cluster the nodes together because maybe they share some spatial or some intrinsic information. So basically, what I'm thinking is that if you cluster them, you should be able to retain some of these characteristics. Now, I'm not an expert on explainability, so maybe there is something that I'm not aware of. But I think that this is the idea. So yes, I think that if you want to perform some explainability task on the network learned at different levels, maybe you're gonna be able to get some useful information.
Okay, great. Yeah, I'll give it a try. Thanks.
I was thinking the same of Balaji, that I think it's a really interesting method for explainability, because if you try to look at the middle graph, maybe you can get some information. So it's really cool. I was also interested in maybe if this technique can be used in autoencoders. What do you think? I mean, I think it never, no one did it so far, but I think it could be interesting to try this technique, at least think at something for the decoder, in the decoder part, and use this kind of technique for autoencoders with
So,
with the
right.
idea of generating something. Could be, what do you think?
But let me get it straight. So basically, what you're thinking is that you might be. I mean, what you want to do is this operation like in the reverse way.
Yeah,
Okay, okay. Well, that is definitely something interesting.
I think it's not easy, but in the simplest way, maybe we can just try to, I don't know, use this technique for the encoder and use the usual. Oh no, we cannot.
No, you know what I'm thinking? The problem with doing the reverse is that in order to do it effectively, you need a number of elements in each cluster which is equal. So basically, you cannot have
Uh, I
clusters that have different cardinalities, because otherwise you don't know how to generate how many nodes to generate from the embedding of one node. If you
you're
know
right.
that you imagine to generate four nodes from that cluster representation, that's fine, maybe.
Yeah,
But if you don't know the number of nodes that you need to create, then it's going to be impossible.
yeah, you're right. You are right.
But it is definitely an interesting idea. Yeah.
Because I think about the fact that you are able to compress an entire graph in a small graph or in a single node with its own feature, and I could be interesting in terms of graph optimization,
Mhm.
like drag discover or something like that. Just a curiosity, in the paper, which kind of dataset they used for their evaluation?
Um, I actually don't remember. Let's have a look at it. So,
In the notebook, you had some protein. So maybe is it the PPI dataset? Or
Uh,
well, actually, I don't really know if it's. I mean, if it's just a placeholder or like
because
if they have used that one. I don't really know. Let's have a look at it.
because the only kind of this type of graph I have in mind are molecules, like ADS, PPA, or, by the way, something coming from biological stuff.
They have actually a protein
Yeah.
dataset, and I guess also this DND is not referred to the table game. It's referred, I guess, to also something related to biology, I think.
But interestingly, there is Reddit that is not definitely not protein.
There is Reddit, yes.
Cool.
Yes.
Cool. Yeah. Thank you for the presentation.
Okay, thank you for listening, and see you next week.
See you next week. Bye bye.
Thank you.
Bye bye. Thank you.